All right. So analysis of variance, ANOVA. This is now our third test statistic that we're learning about. We've learned about Z, and we've learned a lot about T. We've done three different types of T tests. So we've done Z, three different types of T, and now we're doing analysis of variance, also known as ANOVA. And the test statistic for ANOVA is F. So when this course is done, you will know three test statistics, Z, T, and F. You will have calculated Z and T a lot, and you will know conceptually some things about F. So the reason why we care about analysis of variance, the reason why ANOVA exists is, well, its main function is to deal with the experimental designs that t-tests cannot deal with. So if you recall, an independent samples t-test and a paired samples t-test, the amount of conditions for each of those situations was 2. For a paired samples t-test, we had one factor that was within subjects that had 2 levels, 2 conditions, and the paired samples t-test is comparing basically the means of those 2 conditions. Similarly, with the independent samples t-test, we have one factor that's between subjects with 2 levels, and the independent samples t-test is basically comparing the means of those 2 conditions. So the most amount of means that we've been able to compare up to now is 2. In fact, basically every statistical test we've done, Z and T, we're basically comparing 2 things. We're comparing one number to another. We're always, for all Z and for all T, you're always comparing 2 things to each other to see if there's a significant difference between those 2 things. F deals with more complex experimental designs where you might be dealing with 3 things that you want to compare. And this makes sense because in actual practice in psychology and in most fields of science, it's actually very rare that you have a study where there's only one independent variable with 2 levels. It's much more common to have a study with like one independent variable with 3 levels, or maybe an independent variable with 4 levels. And I'll show you an example. Here's an example of an experiment where you would have to use ANOVA to compare means. I'll go back to that previous slide in a second. This is a study where we have one factor, one independent variable. We call it something like type of distraction. And in one situation, there's no phone distraction. In another situation, there's a handheld phone distraction. So you're talking on the phone while you're holding it in your hand. And another one, hands-free phone, and you're talking to us. So we have 3 different conditions. And these numbers down here represent a driving score. So you take like an obstacle course or some type of driving test. And we want to see how does the driving score, how is it influenced by whether there's no distraction at all, whether you have a handheld phone that you're talking on or a hands-free phone that you're talking on. How does performance change among these 3 conditions? You couldn't use a t-test to compare the means here because the t-test can only compare 2 conditions at a time. And there's 3 conditions here. So you need ANOVA. And so a common kind of response the students or people in general have is, okay, why can't you just we have those 3 conditions. Why can't we just do a whole bunch of t-tests? For instance, why can't we compare these 2 conditions with a t-test to see if there's a significant difference? Then we could compare these 2 conditions with a t-test, see if there's a significant difference there. And then we could compare these 2 conditions with a t-test. That would be 3 total t-tests. Why can't we basically just break down these 3 conditions into 3 t-tests, that is 3 pairwise comparisons, and then look at the results of each of those 3 t-tests, each of those 3 separate pairwise comparisons? And the answer is, we can't do that. We can't use multiple t-tests because this increases the likelihood of false positives. I'll point out here, I think the book does a decent job talking about false positives and why ANOVA is important to prevent them. And I'll kind of state some of the things that the book talks about, though the book does do a good job explaining this, I think. Remembering back to when we do a single t-test, the alpha level tends to be 0.05, 5%. And basically what the alpha level represents is this is the likelihood of a false positive. If you do an experiment and you do a t-test, 5% of the time, that t-test is going to show, yeah, we have a significant difference, even though there really should, even though in real life there should not be a statistically, because of just probability and just chance fluctuations in the data. If you do a t-test with an alpha of 0.05, 5%, then that means that if you do 20 t-tests, one of those is likely to be significant, even if the phenomenon that you're studying is not a real, even if there's not a real difference, even if in real life there is not a difference between those means. 1 in 20 times, that is 5% of the time, if you have an alpha of 0.05, you're going to find a significant difference by chance alone, a false positive. And so the problem with, if you have data like this, just doing 3 t-tests, one here, another here, and then another here, is that each time you do that, you have to apply that 0.05, that 5% probability of a false positive. And basically what happens is, if you do 3 t-tests, we've increased the likelihood of us getting a false positive to unacceptably high levels. And this is where the book does this is a figure which the textbook provides me in like the slides for the teacher. And it basically shows how the probability, type 1 error is basically a false positive. And if you're just comparing 2 means, you'd use a t-test. The probability of a false positive is just 5%. But if you have 3 means, like our current example, no phone, handheld phone, hands-free phone, you would need 3 t-tests to compare all 3 conditions with pairwise comparisons. And if you do that, according to, I don't know exactly how the textbook came up with this number right here, but according to the textbook, if you analyze those 3 condition means with 3 separate pairwise comparisons, that is 3 separate t-tests, you will have inflated your alpha level to around 14%. And it gets even higher. So if you have like 7 means, then according to the textbook, comparing all 7 of those means with pairwise comparisons, that is t-tests that compare 2 means at a time, that would require 21 t-tests, in which case your likelihood of a false positive would be around 66%. So the more amount of conditions that you have to compare, the worse it gets if you're just comparing all of those conditions with pairwise t-tests, that is, of t-tests which compare 2 means at a time. And so the purpose of ANOVA is to compare all 3 means of all 3 of these conditions at the same time. Instead of breaking it down into pairwise comparisons, where you compare this, and then you compare this, and then you compare this. And ANOVA, instead of doing, like in this example, 3 pairwise comparison, it compares all 3 means at the same time. And it does so keeping the alpha level at 5%. Instead of inflating the alpha level by doing a bunch of increased amount of t-tests, we just do 1 f-test, 1 ANOVA, and the alpha level is maintained at 5%. And so this chapter is all about how do we do ANOVA. This is basically a way of comparing all 3 means at the same time without having to break it down into pairwise comparisons. So some basic terminology. Some of this is review, some of it's new stuff. I've been using the term factor. I feel like I'm pretty sure I defined this way back in week 1 of school, but just in case we forgot, a factor is basically means independent variable or quasi-independent variable. A factor in stats, IVs and QIVs are treated the same. And so factor basically means it's an IV or QIV. We don't care whether it's an IV or QIV. Factor is basically another word for independent variable, or it's another word for quasi-independent variable. The levels are the individual conditions or the individual levels that compose a given factor. So in the example I just gave you, no phone is a level. Handheld phone is a level. Hands-free phone is a level. And I'm basically using the term level interchangeably with the word condition. So these terms confuse students a lot, but the difference between these 2 terms is important. One way ANOVA is when you're doing a ANOVA where there's only 1 factor. And this is what we'll be doing in this chapter. If you take a methods course, hopefully, usually a methods course will talk a good deal about factorial ANOVA. And in a factorial ANOVA, it's a situation in which you have two or more independent variables. So in this class, we've almost always been dealing with very simple experimental designs where we have only one factor. Like the current example, type of distraction, no phone, handheld phone, hands-free phone. That's one factor with 3 levels. But it's very common in actual psychology and in many fields of study to have, instead of just having one factor, you would have like 2 factors. So an example of a study that would have 2 factors, if we're interested in differences between men and women in type of distraction. So one factor would be type of distraction, no phone, handheld phone, hands-free phone. Another factor would be biological sex, men and women. That would be an example of a study in which we'd have to use factorial ANOVA because we had 2 factors. Biological sex would be one factor. The other factor would be type of distraction. So that's more, we're not actually, I want you to know factorial basically means a study with 2 or more factors. One way means a study with one factor. What we'll be dealing with in this class is one-way ANOVA, one-way designs. But factorial designs, I'm bringing this up because factorial designs are way more common in psychology than one-way designs, and they're more important, arguably. All of my published studies, the big analyses in the study were factorial analyses. And like right now, I'm reviewing an article for a journal, and the main analyses in this study, there's 2 experiments in each one. The main analyses are factorial ANOVAs. So factorial ANOVAs are really important in practice, but they're a little more complicated, and so they're usually weighted to talk about until methods. We're going to focus on one-way ANOVA. Once again, one way means we only have one factor. So we're going to be going with this current example where we have the dependent variable in this example that I've been talking about today, like driving performance through an obstacle course. The better you drive through the obstacle course, the higher your score. The factor, or the IV in this case, type of phone distraction, no phone, handheld phone, hands-free phone. This would be an example of a study of a one-way ANOVA. And it's between subjects if you assume that people are randomly assigned to only one of the 3 conditions. It would be considered within subjects if on day 1, a person does the obstacle course with no phone. On day 2, they come in and do it with a handheld phone. On day 3, that same person comes in and they do it with a hands-free phone. That's within subjects. We're just going to talk about the between subjects situation, which we assume people are randomly assigned to only one of those 3 conditions. Once again, there's the data. I've already showed it to you before, so we're not really going to look at it for too much longer here, but there it is again. So now we're going to talk about the null hypothesis, which is kind of an extension of what we've been dealing with in previous null hypothesis. In general, the null hypothesis means there's no effect. There's no difference among the means that we're comparing. If you think back to what we did for independent samples t-test, the null hypothesis, I gave you kind of 2 forms. The main form was mu1 equals mu2 for the null hypothesis for the independent samples t-test. The other form for that one was using an algebraic manipulation of moving that mu2 over to the other side of the equal sign using subtraction. Mu1 minus mu2 equals 0. But in the basic form, independent samples t-test, the null hypothesis was mu1 equals mu2. The reason we had 2 mu's in the independent samples t-test is because we had 2 sample means. Mu1 represents one sample mean. Mu2 it represents the other sample mean, and we're comparing those. Mu and the null hypothesis says there's no difference for independent sample t-test. Mu1 equals mu2 because there's 2 means. Here, though, in this current example, we have 3 conditions. So we're going to have 3 means. The null hypothesis says there's no difference among those means, and so the null hypothesis is typically stated like this: mu1 equals mu2 equals mu3. If there's no effect, then the means of our 3 conditions should be about the same. This is a good way of writing it in words. The means of the groups do not differ from each other. This is the null hypothesis. The alternate hypothesis, which is also known as the research hypothesis, is there is at least one mean difference among the groups. We have 3 groups, so if we want to use our specific example, we could say there's at least one mean difference among the 3 groups. Please note that this research hypothesis, there's no equation anywhere on this. And that's because once you get to ANOVA, writing the research hypothesis starts getting really complex. And although it's technically possible to write out the research hypothesis in equation form, it's more difficult than is worth the time for us to spend doing in this class. And so if you are asked about the research hypothesis for a one-way ANOVA, the alternative hypothesis for a one-way ANOVA, the answer is basically just writing it out in words. The answer is absolutely not, and I will repeat this, the answer, it would be wrong if you put the alternate hypothesis for ANOVA is mu1 does not equal mu2 does not equal mu3. That is actually not correct. That is not the research hypothesis. That is different than this. The research hypothesis, once again, is there's at least one mean difference among the groups. Potentially, there's several things that can be consistent with this. There's at least one mean difference among the groups. There are several things that could satisfy this research hypothesis. One of those things is mu1 does not equal mu2, which does not equal mu3. That is, all of the means are different from all of the other means. But that's only one possible outcome that is consistent with the research hypothesis. Another outcome which is consistent with the research hypothesis, which is much more typical, is that some of the means differ from some of the other means, but possibly some of the other means don't differ from some of the others. So giving an example would be, for instance, mu1 does not equal mu2, but mu2 does equal mu3. So one of the mu1 is different from mu2, but mu2 is not different from mu3. That's consistent with this research hypothesis. At least there's one mean difference among the groups. So there's all of these these are like the two main different scenarios that are consistent with the research hypothesis, but you can break this one down into many, many different like sub parts. There's many different variations of this. For instance, mu1 equals mu2, but mu2 does not equal mu3. Or mu1 equals mu2, mu2 equals mu3, but mu1 does not equal mu3. There's many different variations here where some means differ from others, but some means do not differ from others. So instead of writing all of those different variations when we're writing the research hypothesis, just write it in words. Say there's at least one mean difference among the groups. Probably the safest way to go, and that's usually how it's taught in various textbooks. Any questions or comments so far? All right, moving on. So we've done the null hypothesis, done the research hypothesis. Now it's time to look a little bit look at the equations for F. Now I'm going to show you the equations for F, but the deal here is that you're never actually going to have to calculate F. You've calculated T, you've calculated Z, but you're not actually going to have to calculate F. I've looked at the test, and what you will have to understand some conceptual things about F, but you will not actually have to calculate F. And I'll tell you more about that next class, about stuff that's going to be in the test. But I still want to talk about the overall structure of F because that helps you understand some of the conceptual things about it. So here's F up here. There's, variance between treatments, variance within treatments.
I have a question.
Yes,
Sorry.
please, go ahead.
I thought the test isn't the test Wednesday?
I'm moving the test to give you more time.
So the test is Thursday now?
No, I mentioned this at the beginning of class. I'm going to make it so you can take the test anytime during your finals week.
Oh, okay. Sorry, I missed that.
No, it's okay. Yeah, it's okay. I'm trying to be helpful here so that you don't have as many things that you have to be doing this week, so we're not as crammed for time. So I'm just going to give you. Originally, it was going to be. This is a last-minute change. Originally, it was going to be next class, but I've decided that instead of that, I'm just going to do a review for the test Wednesday and finish up a little bit of stuff on ANOVA here that I feel like is important. And then over the weekend, I'll post the test, and you'll have basically 5 days to do the test. And I'll send out an email about this, formalizing the stuff that I'm saying here. Yeah, no, thanks for asking.
Okay, thank you.
Yep. Okay, so going back to this, here's basically the F ratio, the F statistic. And notice that there's words here, MS between and MS within. These are basically words that are standing in for formulas. We'll go over those formulas, but you will never be responsible for them in this class. In my other classes of statistics I've taught, I've definitely required my students to know these formulas and to do calculations and stuff, which personally I find to be really fun. But that's just not the way we're doing it here at KU, and so you will not have to be doing any of these calculations. But I still want you to understand conceptually what's going on here. So the first really important conceptual thing here is that if you look at the F, it's conceptually very similar to T. So this is the independent samples T that we've been dealing with recently. And if we look here at the T, remember the independent samples T, we're comparing the means of two different conditions. And so the numerator of T is M1 minus M2. And so for T, the further apart those two means are from each other, the bigger the numerator gets. If M1 and M2 are the same number, then the numerator is really, really small. It'll be 0. If M1 and M2 are really far apart from each other, then you get a big number in the numerator for T. The same thing occurs with F. MS between basically is the number. There's a formula which this represents. There's a formula for MS between, but what it represents is what is the magnitude of difference among all of the different means of our conditions. We have 3 means in the current example. So on average, what is the average distance, the average magnitude difference of each of the 3 means that we're comparing? The bigger the difference between our 3 means, the bigger MS between gets. Just like when we're doing a t-test, the bigger the magnitude difference between our 2 means, the bigger the numerator gets. The bigger the difference among the means, the bigger the numerator gets. Just like in T, the bigger the difference between our 2 means, the bigger the numerator gets. Similarly, in T, the denominator was standard error. Now, standard error is kind of a complicated thing, but I'll remind you the basic formula for standard error is standard deviation, sample standard deviation for T, divided by the square root of n. So standard error is very much related to standard deviation, a measure of variability. Basically, the denominator is a measure of variability. And basically what it's doing, the standard error, what it's doing kind of conceptually, is it's taking basically the average amount of variability in each condition. The average amount of variability in each condition. Same thing with MS within. We have 3 conditions now, but we're basically taking the variability in condition 1, the variability of condition 2, the variability of condition 3. We're basically taking the average of the variability in each condition, and that is the denominator. Same basic thing that we were doing for T. So the structure of F is very analogous to T, and the structure of T very analogous to Z. For all 3 of our test statistics, Z, T, and F, all 3 involve a ratio where you're taking a numerator divided by the denominator. The numerator always represents the magnitude of the difference of the means we are comparing. The denominator always represents a measure of variability. And it kind of says that here once again. The numerators represent the influence of the treatment, and the denominators measure the influence of sampling error, which basically sampling error is analogous to the amount of variability. The amount of variability on average within each condition. And so I'll show you some examples to make this more concrete. First, though, I do want to talk about degrees of freedom, because we're going to talk a little bit about the F table next time, Wednesday. And one thing which makes F, there's a typo there. One of the things that makes F a little bit complicated is, it's not chapter 12. One of the things that makes F a little bit complicated is that there's 2 degrees of freedom that you have to calculate. In T, there was always just 1 degree of freedom that we had to calculate. For one sample T, the formula was n minus 1. For the paired samples t-test, the formula was n minus 1. For independent samples t-test, the formula was n minus 2, because we had 2 sample means for the independent samples t-test. But in each case, for the T's, there's just 1 degrees of freedom. For F, there are 2 degrees of freedom that you have to report. Something called degrees of freedom between, also known as degrees of freedom numerator, meaning the top part of the ratio, and degrees of freedom within, which means the bottom part of the ratio, degrees of freedom denominator, or degrees of freedom within. And the formulas for these are shown here. K minus 1 is K means the number of groups or the number of conditions. So for our current example, that would be 3 minus 1, which equals 2. So our degrees of freedom between for the current example would be 2. Degrees of freedom within, that N means the total sample size minus the amount of groups. So for that would be 15 minus 3. The total sample size was 15 people. We had 3 conditions, each with 5 people. 3 times 5 is 15 people, 15 scores, minus K, the number of conditions. 15 minus the number of conditions, 3 equals 12. So our degrees of freedom between was 2, 3 minus 1. Our degrees of freedom within was 12. 15 minus 3 equals 12. And so those numbers are helpful because eventually, we're not going to do it today, but next class I will show you a little bit about how to use an F table. I mean, just like what we did with T, if you want to look up your critical T and then the T table, you have to have a critical T, or you have to have your degrees of freedom. And then you use that degrees of freedom to find the critical T in your T table. Same thing with F, except for the F table, you have to know 2 degrees of freedom, the degrees of freedom between and the degrees of freedom within, or degrees of freedom numerator and degrees of freedom denominator. You look up those 2 things and your alpha level in the F table, and it gives you your critical F. I'll talk more about that in a second. You do not need to know these at all. These are things that if I was making you do the calculations, you would need to know this. I wish we had time to do this because it's fun, but we just do not have time to do this. So once again, instead, I'll just show you this is the F ratio. MS between, this represents the magnitude of the difference among our 3 means, or however many means we have. MS within represents the average amount of variability within each condition. And I will show you more. I'll show you examples that illustrate what these 2 things measure in a second. Just for the sake of showing you, these are the formulas that we would be using if we were calculating MS between, that is the numerator, and MS within, the denominator, by hand. Here are the formulas right here. The book actually talks about these. It does a particularly good job talking about SS between, which is part of calculating MS between. All of the F, the numerator and the denominator of F always involve sum of squares, just different ways of calculating sum of squares. These look intimidating. Really, they're not that bad. And if you do want to know about them, the book does. I've read textbooks that do nearly as good a job talking about this one in particular. Oftentimes, they don't talk about this one at all in textbooks. For whatever reason, the book does a pretty good job talking about all of these. And so, yeah, you can take a look at those if you want. But yeah, you do not need to know these at all. These are the underlying calculations. I will show you the results of these calculations, that you will not have to know these or use these. So a couple things generally about F. These are some of the conceptual things that I know there's a question about this on the test, for instance. If you have no effect, that is, if the mean difference among your means is 0, that is, all the means of your 3 conditions are the same, then the F number you're going to get when you calculate F is going to be about 1. So this is different than what we did in Z and T. In Z and T, if you have no difference among the means that you're comparing, your T value would be 0. Same with Z. If there's no difference between the 2 things you're comparing for Z, then your Z value will be 0. For F, though, things are different because of the different calculations. And if you have no effect whatsoever, your F value will be basically 1. But for the research hypothesis, like that is, if you the further away you get from 1, that is, the bigger the magnitude of F, the more likely you are to say, yeah, the H1 is true. That is, we reject the null hypothesis. This is similar to what we did with Z and T. For Z and T, the further we got from the middle of the distribution, that is, the further into the tails our Z and T's were, that is, the bigger the Z and T away from 0, the more likely we were to reject the null hypothesis. Same thing with F. The bigger our F, the further our F value is away from 1, the more likely we are to reject the null hypothesis, the more likely we are to say there is a significant difference among our means. So we're going to talk about this in more detail next time. I'll just tell you, yeah, there's really, I've mostly said most of the stuff already. If there's no difference among our means, the F value will be around 1. I guess this is an important thing I haven't mentioned yet. Mathematically, all of our F the numerator and the denominator of our F ratio are computed using sum of squares. And when you're in sum of squares means we're squaring stuff. And when you're squaring stuff, it's impossible for a number to be negative. We didn't square stuff when we were doing T and Z. So we could get negative numbers in the numerator for Z and T. But that's not the case for F. For F, the numerator always has to be positive and the denominator will always be positive as well. So F's are always positive. Remember, for Z and T, we had to deal with the left side of the tail where the numbers could be negative. That's not the case for F. There's only one tail for F, and it's always the positive side of the tail, which actually makes things a little easier. F is more complicated in most ways, but one of the nice things is F is always positive. You never have to worry about the negative side of the tail. And yeah, we'll talk about the F table next time. The one thing that I will say about the F table is that it gives you critical F values. And if the F that we calculate is bigger, if it exceeds the critical F value, which is in the F table, we reject the null hypothesis, just like we did with T. In the T table, we looked up a critical T. We would calculate our T value. If our T value exceeded the critical T, that is, if it was further into the tail relative to our critical T, then we would reject the null hypothesis. Same thing for F. If our F value is bigger than our critical F value, then we reject the null hypothesis. So here's what the kind of the distribution looks like for F. Remember, for Z and T, it was a symmetrical distribution. We had a left tail and a right tail. But for F, it can only be positive. And so you see there's only one side of the tail here, which makes things a little easier. For this particular example, which I got from a different textbook, you would have a critical F value right here, 4.94. And then the rejection region would be this blue area. So then if your F statistic that you calculated was bigger than 4.94, then you would reject the null hypothesis. This is just a different example. So here's the example that we're dealing with today for our the example type of distraction, 3 levels, 15 total participants. So what I'm showing you here, well, there's several things. Here's the 3 conditions. Each of these numbers represents the driving obstacle course score, how well people did on driving on the driving obstacle course. A bigger score means a better performance. The mean of condition 1, no phone, was 4. So these people without a distraction at all, no phone, no distraction, their driving obstacle course score was good, 4, high score. The people in this condition, their score was relatively lower, score of 1, that was their mean score. And the mean score for people over here was 1 as well. So just looking at this, it appears that when there's no distraction at all, you score well in the obstacle course. But when there's any type of distraction, it looks like you're performing worse. We want to do an ANOVA because we want to see, are these means significantly different from each other? Are these 3 means different enough from each other that we're willing to conclude, yes, there is a significant difference? And so I'm telling you kind of the answer of this before I've gone through the work. The F ratio, if you were to analyze this, is 11.25. The reason, or the math that kind of produces this, is we get a numerator, an MS between, of 15, and we get a denominator, an MS within, of 1.3 repeating. 15 divided by 1.3 repeating gives you 11.25. So now I want to show you a little bit, without going into super detail about how we got these 15 and 1.33, what these numbers represent. And remember, this 15 represents the magnitude of the difference among the 3 means. The denominator, 1.3 repeating, this represents the average amount of variability within each condition. Okay, so here is the calculations that I used for MS between. You don't need to know how to do these, but this is me showing my work anyway. Please note that it all is based on a sum of squares calculation. Like I mentioned before, there's the sum of squares. And then ultimately, when we do some math, we get the MS between equals 15. And I plug that in to right here, we get 15. So the next slide, I'm going to show you how I calculated this 1.3. So here's the MS within. We have, once again, a bunch of different scores right here. We add those together to get a sum of squares within. We do some math. and we get our MS within equals 1.3 repeating, which is right here. We plug that in, we get, when we divide 15 divided by 1.3 repeating, we get, once again, 11.25. So now what I want to show you is I'm going to take the same example, which is based off like a real study with real data, and now I'm going to manipulate it. I'm going to fudge the data. I'm going to change the data, and I want to see how does the F ratio change depending on changes in the data. And so this is example 2 now. And please note that the sample means have changed. Now the sample, okay, so this condition is the same. The no phone condition, the sample mean is still 4. But now the mean for the handheld phone condition is 4. It's gone up by 3. And the mean of the hands-free condition has gone up by 2. It's now 3. So it used to be 4, 1, and 1. Now it's 4, 4, and 3. The way I've done this, the way I've changed the data, if you look, these data remain the exact same. That's why you still get the same sample mean of 4. What I've done here is I've taken the original handheld phone condition and I've just added 3 to every one of those scores. So if we go here, this is the original. This is example 1 that we've been dealing with. 0, 1, 3, 1, 0. To get example 2, which is what we're looking at here, I've just added 3 to each of those to get 3, 4, 6, 4, 3. And that now we have if you add 3 to each number, it makes the sample mean 3 bigger as well. And so now the sample mean is 4. For this one, I just added 2 to the original data. So the original data were 1, 2, 2, 0, 0. Now we have 3, 4, 4, 2, 2, because I've just added 2 to each one. The sample mean used to be 1, but now that I've added 2 to each score, the sample mean is 2 bigger. And so now the sample mean here is 3. And so we have these 3 means, and we're going to compare them using an ANOVA. And we get an F ratio now of 1.25, so a smaller F value. And if you look at the reason why we have a smaller F value, you notice that the MS between is now 1.6 repeating. It used to be 15. In example 1, it was 15. Now it's 1.6. It's gotten smaller. The MS within, on the other hand, has actually stayed the same. MS within has not changed. And I'll just tell you, the reason why the MS within hasn't changed is because the average amount of variability has not changed. I've added the same amount to each value here. I added 3 to each one here, which keeps the variability within this condition the same. I've added 2 to each score here, which keeps the variability here the same. So the average amount of variability within each condition is the same. So 1.33 is what it is now, the exact same as what it was in the original example 1. Before we continue, I need to ask you an important conceptual question. If I had an example of a data set with 5 scores, where the mean of those 5 scores was 4, what would be the set of 5 scores that would produce the absolute smallest amount of variability possible? What combination of 5 scores would give me a mean of 4 with the smallest amount of variability possible? What 5 scores could I add together to get a mean of 4, where if I add up those 5 scores, or if I take the variability of those scores, there'll be virtually 0 variability? Can anyone figure this out? Pretty tough question, but it's an important one. Sorry, say that again.
Is there all 4?
Yes, thank you. Good. It's a tough question, but yes, that's it. If you do 4 plus 4 plus 4 plus 4 plus 4, that's 5 4s. The average of those numbers is obviously going to be 4, but the average distance of each of those 4s from the mean is 0. So our variability would be 0. So if we did that, if that was the way it was, if this condition right here was 5 4s, this condition right here was 5 4s, this condition right here was 5 3s, then the MS within would be 0, which would cause the overall ratio to be infinite, which would cause problems. But that rarely happens where all the scores, in fact, that basically never happens where all the scores are the same within each condition. But that illustrates kind of what the MS within is doing. If these numbers had zero variability, that if they were all fours, if these numbers had zero variability, they're all fours. If this had zero variability, they were all threes. Then the MS within, the denominator would be zero, representing the fact that those numbers, the average condition has zero variability. But as I mentioned, in this current example, the variability just hasn't changed. The reason relative to example 1, because I just added the same amount. I added 3 to each score from example 1 to get these 3 scores. I added 2 from example 1 to get these scores right here. Now, once again, though, the MS between has changed. In the original example, MS between was 15. MS within was 1.3, repeating. In this example, now, MS between is 1.6, and our MS within has remained at 1.3. And a question I have for you is, why did MS between get smaller? Anyone know why did the MS between get smaller? You don't need to know the calculations exactly. Conceptually, though, you should be able to understand, why did the MS between get smaller?
There's less difference between the means.
Yes, good. Very good. Yeah. In the original example, where we had a big MS between of 15, our means were 4, 1, and 1. The relative difference between 4, 1, and 1, those relatively bigger difference, compared 4, 4, and 3. These 3 means right here are, all right on top of each other. There's small difference among them, 4, 4, and 3, very little difference compared to 4, 4, and 1, where there's relatively bigger difference. The difference here is 4, 4, and 3, relatively small difference. And so the MS between reflects that. MS between measures the magnitude of the difference between the 3 means. When there's a small difference among the 3 means, MS between is going to be small. When there's a big difference among the 3 means, MS between will be big. That's where we'll call it a day, because that's where I left off with my other class. We have a little bit more on ANOVA to talk about, including a couple more of these examples. We'll talk a little bit about the F table next time. I'll show you how to do this in SPSS. And then I'll give you a study guide for the final test next class as well. And as I mentioned at the beginning of class, I'm moving the test. So instead of making you take it Wednesday, like originally planned, I'm going to post it this weekend, and you will have all of finals week to take it. If there are problems where a student has to take it for whatever reason on Wednesday, we can email me and we can make plans. But I imagine for most people, you'll like the fact that the test is moved back. But if that does cause scheduling problems for a student, definitely feel free to send me an email. Otherwise, yeah, you guys are excused. I know some people had some questions about homework 5. I definitely have some time right now to talk about it. So stick around if that is you and you want to talk about it, or if you have anything that you want to talk about. Otherwise, I'll see you Wednesday.